All right, section 1.2 we started last time. We had taken a look at some different kinds of patterns, and the patterns that we are on at this point are figurative numbers. So figurative numbers are based on visually geometric patterns. Their examples are neither geometric or arithmetic, and such numbers can be represented by dots arranged in the shape of certain geometric figures. So I'm going to show you two examples. These are not the only two figurative numbers. You can create figurative numbers in kind of whatever shape you want. Okay, so triangular numbers. We're just going to draw the pictures for these. I think I need to change this. Let's try it. So the first triangular number has one dot. The second will have three dots, something like this. The third one, like this. Kind of looks like, you know, when the cheerleaders do pyramids, right? The fourth one looks like this. We'll do one more. The fifth one will have how many dots on the bottom? 5. Like that. All right, so obviously there is a natural kind of correspondence with the shape and how many dots it has, and we could count them. So that's what we're going to do next. If we were to count these, what would the numerical pattern be of the number of dots in each figure? Like the first one's 1. What's the next one? 3. 6. 10. 15. Now, I stopped my picture here, and so I'll stop my number pattern here, but I want to show you something cool that we talked about last time with this number pattern. So here's my number pattern. If I were looking for an arithmetic sequence, remember arithmetic means adding, what would I need to do to get from 1 to 3? Add 2. 3 to 6? 6 to 10? And 10 to 15? Add 5. And do you see a pattern with the numbers of the additions that I just wrote down? Yeah. So if I wanted to go to the next figurative number, I would add 6, and that would give me 21. And we could continue going with that. And you saw the pattern with the 3, 4, 5, 6, and that's great, but the reason you saw it is because right down here, these are all +1s, right? And we talked about last time when we have the ability to do this twice or 3 times or whatever, to do the differences, then it has a name. So since this one was the same the second time we did it, these has a same second difference. The second differences are the same, they're all 1s. We saw the pattern before we got there, but it's the second differences that are all the same that created the ability for us to see that pattern. So these are figurative numbers. Triangular shaped ones, anyway. We will do square numbers next. So square numbers, same idea. Here's my first one. Here's my second one. There's my third one. My fourth one. And what in the world will my fifth one look like? 5 by 5. That's right. Might be the best figurative numbers I've ever drawn. For real. All right, we have a numerical pattern here, just like we did with the triangular numbers. So what is the numerical pattern that you see happening here? 1, 4, 9, 16, 25. And aside from addition and, like arithmetic and geometric, you know this pattern because you can see it, right? What do you see happening here? These are squaring. And Rebecca, does that kind of make sense based on the fact that these are called square numbers? Yeah, I mean, like there's obviously a relationship there. That's why it's happening. But I do want to show you that it actually still works the way that I did with the last pattern. So let's look at this as though it were an arithmetic sequence. Okay, we're trying to find the addition that we'd add each time. Because I'll tell you what, if you saw the pattern like this, you might say, those are just squares, right? It's just whatever the number is squared. But if you saw the pattern and it looked like this instead, I don't think you could do that. I don't think you would look at this and just say, I know what that is. That's the squareds minus 1. I mean, it is the squareds minus 1. Oh, I missed one. The last one should be 35. Sorry about that. It is the squareds minus 1. But you probably wouldn't look at that and just automatically jump to that as being what's going on, right? So it still works. This one I just wrote down and works too. If we look at the arithmetic possibility here. So how do you get from 1 to 4? Add 3. 4 to 9? 9 to 16? And 16 to 25? Oh, you're telling me I skipped one. That's why you guys looked at me funny before. You're fine. 4, 7, 9, right? Sorry, down here I missed one, didn't I? It's supposed to be 24 and then 35 if I was looking at the pattern before. Okay. These aren't the same, right? I had 3, 5, 7, 9, but there's obviously a pattern there, and in fact, if you tried to do the second differences, you would see it very quickly. What would you find? They're all plus 2s. Now, we didn't go much further than this, but I know you know that the next one's supposed to be 11, and then it's supposed to be 13, and then I know you know that. But if you went down far enough, right, if it took the third differences or the fourth differences to actually do that, what you do is you just work your way back up the difference chart. So it would look something like this. In order to get from 9 to the next number, I need to add 2. 9 plus 2 is 11, and then I can take that 11 and add it to the 25 to get me 36. Okay, so you can work from the bottom up. Once you've established the relationship and looking for a pattern, that's what you're going to be looking for. There's a specific problem that you're going to have. I don't remember if it's group work or homework, and there may be one even on both. And it's in section A, and every time that somebody does that problem, I always get answers without any work. And it's a problem like this, where the only way you got an answer without any work is if you flipped to the back of the book, and you didn't know how to do it, and so you just wrote it down. It's a second difference or third difference problem. So you're looking for this subtracting pattern, and that's what you're looking for to do that problem, okay? So if you don't see the pattern right away, try a second difference, try a third difference, see if you can find the pattern doing that. All right, this is a fun example. It's a real life thing that happened. 2011 is when our university created the Hurley College of Science and Mathematics. And it was our first ever meeting before we were part of the College of Arts and Sciences, I think was what I called it. And so we were like in the same college you guys are with your education classes and stuff. We were all part of the same group of faculty, basically. So in 2011, a newly formed Hurley College of Science and Mathematics had a meeting, and on the board, the dean had written 3.1415 ... And she asked us to find the next 2 terms in the sequence of numbers. So without talking to anyone, would like for you to write down what would you say are the next 2 terms in this sequence and explain your reasoning. Okay? So take just a minute, write down what you believe the next 2 numbers should be and why you believe they should be that. All right, somebody tell us what you wrote down as the next two numbers you believe the next two numbers should be, based on what you're looking at. What do you think?
Actually, I have two guesses. The next two numbers, 9, 2, because isn't that the next sequence?
Okay.
Is that numbers in 5? That's actually.
What's your other guess, Catherine?
My other guess is that the next two numbers are 1 and 6.
Okay, so show of hands, how many of you wrote down the first one that Catherine suggested? Did anybody want to write that one down? You thought about it, but you didn't write it down. How many of you wrote the second one? That's usually what happens in this class at this point, is that most people saw the second one. It's kind of a trick question because you're seeing it because, especially in that particular one, because of the things we've been looking at in terms of patterns in this section already, right? Your mind just goes to there. So the first one is what everyone in that whole room wrote down. Any guesses as to why?
Because it's pi.
Because it's pi, and you're looking at science and math people, right? Because of course that's where my brain's going to go. It's pi. I use pi. You know, I know that's about as far out as I really know my digits for it, but you know, I know a few digits of pi. I've used it before, right? I use it frequently. So when my mind goes to 3.141592 and your mind goes to 3.141516, who's right? I don't know, right? I mean, we don't know. I mean, who would be right? All right, so here's the kicker. Inductive reasoning is one of the reasonings we talked about in this section. It's taking a example or a series of examples and trying to form a generalization from it, right? A pattern and looking for a generalization. That's what we both did, all did, in this problem. You took the pattern, 3.1415, and you tried to say, the general process here is, therefore the next two numbers will be, and you guessed. Inductive reasoning doesn't always work, does it? Right? I woke up this morning, I know I gave this example before, but I woke up this morning and I actually checked the weather today because I thought, it's been beautiful the last 2 days, but man, I would hate to not put on something warm today and all of a sudden some cold front came through and I didn't know it was going to. Right? If you generalize a lot, at some point you're going to be cold outside with the weather. Okay? Here, you're generalizing. And based on your generalization, neither one of these answers is wrong. It's because inductive reasoning doesn't always have one specific answer. It's an educated guess based on patterns that you see. Okay, so the part here at the bottom says, what does it tell you about inductive reasoning? Well, inductive reasoning doesn't always just give you one answer. And it doesn't mean that my answer when I looked at and thought of pi and your answer when you looked at it and put the 1, 6, one of them's right, one of them's wrong. It's just that we both used different inductive reasoning patterns to form our conjectures. Because that's what we did. You guys gave a conjecture, a guess, an educated guess as to what you thought was happening next.